Welcome to Ask and Learn.
For this function, we know that our domain is x is all real. Our intercepts, if we substitute 0 into x, we can see 0, 0 is an intercept. For symmetry, there's none. Asymptotes, there's no denominator here, so we can't set that equal to 0 to find vertical. But for horizontal asymptote, what we can do is we can find the limit as x approaches negative infinity, because that would seem like it would find an asymptote for our function e to the 2x minus e to the x. Substituting negative infinity into x, into our x of our function, will give us 0. So we have a horizontal asymptote at y equals 0. And now we can look at the increasing and decreasing intervals by finding the first derivative. So y prime equals 2e to the 2x minus e to the x. All right, that is y prime. And if we set that equal to 0, we can find critical points. So let's factor this out. So that's equal to e to the x times 2e to the x minus 1 equals 0. So that's easier to see. So e to the x equals 0, we can't do that. But for this one, we can see that x is equal to ln of a half. All right, and that's equivalent to negative ln of 2, which is approximately negative 0.693. So that's a critical point, and if we make a little line for our first derivative test, so this is f prime, and this is our critical point, negative 0.693, and we test values to the left and right of it. So smaller than our critical point will give us negative, and anything larger will give us positive outputs. So if it has a decreasing interval and then it goes to increasing, that means that this is our local minimum value here. And if we want to find the y value of this minimum value, f, so substitute into our regular function, into y, so f of our critical point, which was negative ln of 2, that's the precise, that will give us negative 1/4. All right, so that's it for the first derivative test. And now we can test for concavity using our second derivative test. So if this is y prime, we can solve for y double prime, which is e to the x to 4e to the power of x minus 1. And if we set that equal to 0, then we see that our critical point is negative 2 ln of 2, which is about negative 1.39. So if we do the second derivative test, so this is f double prime, we can see that, and we put our value here, so negative 1.39. Anything smaller will give us negative, and anything larger will give us positive. That means that this area is concave down, this area is concave up. And because it's switching signs from negative to positive, we can say that this negative 1.39 is an inflection point. And if we want to find the y value for this point, the exact, as we already said, that was negative 2 ln of 2. So plug that into our function, y. That will give us negative 3 over 16. All right. So this is our second derivative test. This tests for concavity. And now we can graph our function. All right, so we can plot our minimum value first. We said that was negative ln of 2, which we said that was approximately negative 0.693. So that would be, if this is 1, it would be about here. So let's say this is negative ln of 2. This is negative 1. So that's negative ln of 2 and negative 1/4. So if this is negative 1 for the y's, it would be about here, so negative 0.25. So we can say this is our minimum. So that's our minimum value. And our inflection point was negative 2 ln of 2, and that was approximately negative 1.39. So negative 1.39 would be about here. And the y value we said was negative 3 over 16, so let's say that's about here. Let's say our inflection point is about here. So that's our inflection point. Oh, and we said that we had a horizontal asymptote at y equals 0, so let's draw that in. All right, and now we can concave down before negative 1.39. So before our inflection point, it's concave down. And then it hits our inflection point, and now it's going to be concave up until it hits our minimum value. And now it's going to continue being concave up beyond that as well. And it's going to hit, oh, we have an intercept here, don't forget, 0, 0. So minimum value is going to go concave up and continue. This is our curve.